All right. Good morning, everyone. It is 10 o'clock right on the dot. I'll give a minute or so for people to trickle in here to our Design for Off presentation, the first time we've had this. So people are trickling in, John. We've got almost 15 people showing up right now. But I expect that to triple in the next couple of minutes. Level. Oh, they're doing good. All right, let's get started. Welcome everyone who has just joined and who I've said welcome to several times already. It is October 5th and we are going to listen to a presentation from John today from Ecotope, their Design for Off webinar, and I think John's got a compelling case for us. Just some housekeeping stuff at the beginning. You're all going to be on mute this whole time, but there is a questions box. It's either, it looks like this questions box or this little bubble with a question mark in it. If you can't see the toolbar, there should be a little red arrow on at least one of your screens. Click on that and it'll bring the toolbar back out for you to see the questions tab.
And I welcome questions during the presentation. Katie will be monitoring that and interrupting me as we go. So if you've got questions during the presentation, feel free to throw them up there.
Yep, I will be monitoring that the whole time. The webinar is being recorded, so if you have to jump off, you can find the recording on our website within a week or so after this presentation. And there's a little survey at the end that we ask you to take to help us understand if this is the content you would like to see. We also, thanks to Ecotope, have a course coming in 2 weeks on the 19th about the Inflation Reduction Act, focusing on the tax credits for businesses. And then energy management systems, which we did last year, is coming again. We don't have a date set yet. And a lighting design process and retrofit techniques with our favorite Eric Strandberg is coming, but we don't have a date set for that. But lightingdesignlab.com, subscribe to our newsletter, and you will get the newest dates when those come out. And I am going to hand it over to John. Oh, and I didn't say I'm Katie with the Lighting Design Lab, and that's just going to be answering your questions. Make John the presenter, and here we go. Did you get control? There we
go. Great. Well, thanks everyone for tuning in and spending a bit of your morning with me. I am going to talk about Ecotope's design approach for delivering energy efficient all electric buildings. There we go. First of all, just a one slide introduction of who Ecotope is in case you haven't heard of us before. We're a mission driven company. We're leading the transformation of the building industry to energy efficient, carbon neutral buildings. And we have two groups here that overlap. We have a mechanical engineering design group, which delivers super energy efficient all electric buildings. And we have a research group, which is researching new technologies and techniques that are going to be needed to decarbonize the building sector. And we focus on three primary responses to the climate crisis in buildings. First of all, electrify everything. Stop burning fossil fuels in our buildings and switch to high efficiency heat pump systems instead. Second is what I'm talking about today, which is a primary focus on energy efficiency in the buildings, and our design approach to that, delivering that is what I'm talking about today, the design for off. But the reason that that's critical is we need to free up electrical energy to run our transportation sector and to be able to transition our heating fuels off of fossil fuels to heat pumps. And then the third is while we are electrifying buildings, the grid is decarbonizing. Seattle's grid is already decarbonized, but the rest of the country is getting off of fossil fuels. And as we do that, when we use energy starts to matter as much as how much we use. So as the grid shifts to a focus on solar and wind, that timing of energy use becomes really critical. So I'm going to start this with a little step back in history of energy efficiency in buildings, and want to start with thinking about how we delivered buildings before air conditioning. The Arctic building there was built right at the turn of the century as the first electrification of buildings was taking place. So it had to be built to allow for quite a bit of passive conditioning. Punched openings that are set back so that there's some natural shading provided by the building itself, operable windows, pathways for ventilation through the building so that there could be cross ventilation during hot days, high mass construction, tall windows for daylighting, so a lot of passive design. In the 60s, we really started, was kind of the era of air conditioning and cheap energy. And we really kind of moved towards this idea that we could just seal up the buildings and crank up the AC or crank up the heat when needed. And that has kind of set the stage for mechanical design ever since. And one of the factors of that type of design that's really driven high energy use in buildings was this common design practice of perimeter offices and sealed core. So all the important people got perimeter offices with single pane windows that in the Seattle climate almost always need heating or they need cooling if the sun's shining on that big wall of glass. And a large core where the people that did all the work sat under 2 watts per square foot of incandescent lights and with a lot of equipment load. So that area was pretty much always in cooling. And this really drove the development of mechanical design and drove high energy use in buildings. So we look at, I'm going to be talking about EUI, Energy Use Index, in thousands of BTUs per square foot per year. Seafirst building, kind of one of the first skyscrapers in Seattle, the box that the Space Needle came in. EUIs we looked at it in the early 80s, and it had an EUI of 125 at that time. Really the bad old days of cheap energy and big VAV systems. In the early 2000s, the Seattle City Hall, first major LEED building in Seattle, cut that energy use about in half, with daylighting and shading, high efficiency VAV, fairly run-of-the-mill design, but delivers, cut that energy use about in half from the bad old days. A little later in the 2000s, Alley 24 got a lot of attention as a LEED Gold building. This, in my opinion, is kind of it showed what you could do with VAV. Had underfloor air, heat recovery from the server rooms, very efficient lighting design, got that EUI down to about 50. And then we see later the Bullitt Center come along, really showing just about the limit of what you can do with an office building in terms of driving down the EUI. Super efficient envelope and triple pane windows, geothermal heating system, high efficiency heat recovery ventilation, automated shades, a lot of lighting controls and so forth, driving that EUI down into the teens. And we're probably not going to do a whole lot better. We can shave a bit more off of that probably in the future, but this was also at the time a very expensive building, and so I think people kind of tend to say, well, not everybody can do what the Bullitt Center did because we don't have that kind of budget. But I'm going to show you how it's really about design approach, and we can approach those low EUIs with less expensive design. And I throw this slide up there to kind of remind us that some of those really old buildings have can deliver pretty low EUI based on some of those intrinsic qualities of high mass, smaller glazing openings, and zonal systems. So if we think about what happened in energy code development over the last 40 years, in the late 70s, early 80s, we had what we were calling the energy crisis, brought about by the Arab oil embargoes of the 1970s. And this brought a focus to energy efficiency as a real thing, kind of started the energy efficiency industry that has delivered a huge amount of energy availability, particularly in the Northwest, over the last 40 years. We haven't built any major power plants to support all of the growth that we see in the region over the last 40 years. And that's because of this energy efficiency industry and development of energy codes. So lighting has gone from about 2 watts a square foot in those big commercial buildings down to really less than half a watt a square foot. So less than a quarter of the energy being dumped in from the lighting circuit. And similarly, there's been huge progress on building envelope efficiency, going from really uninsulated single pane construction to very high levels of insulation in the walls and very low, driving towards triple pane window requirements in Seattle anyway. So again, probably a quarter the heat loss at the envelope. There's been some focus on mechanical system efficiencies in terms of focus on the efficiency of the widgets themselves. for example, moving from gas boilers in the 70% up into the 90s, but very little has been done on driving mechanical design practices, other than the dedicated outdoor air system requirements that Ecotope helped bring into the energy code several years ago. But design, as I'm going to show, is really the critical factor for driving energy use down from where it is now to where it could be. So if we look at commercial buildings in the U.S. and energy use index, we can see that there has not been a lot of progress since there's a little drop in the early days of the energy crisis, and then really no movement until the early 2000s at all. Energy use in commercial buildings just stayed constant. And then over the last 20 years, we've seen a slight reduction as those energy codes have started to begun to drive down energy use in buildings. And a lot of that is due to lighting efficiency. That's really been the big change that's happened over the last 20 years, is the transition to LED. But the national average for office buildings is still up there at 66. And Seattle is actually doing quite a bit better because of the advancement of our codes and climate and so forth, down around 43. But the 2030 target in Washington State is down in the low 20s. So we've got quite a ways to go to get down into the areas that we're shooting for to be able to decarbonize our economy. So the question is, how do we get there? And if you look at where does the energy go in a commercial building, we've done a good job on the lights in the red there. Plugs and other uses, there's still efficiencies to be made there, but we don't have a lot of control over that as mechanical designers, and it's hard to get at that with energy codes. A lot of that is stuff that's brought into the buildings. But the big chunk of energy use is the HVAC. It's not the lighting designer's problem anymore. It's not the architect's problem anymore. It's the mechanical engineer's problem. And where that stems from is kind of our typical approach to HVAC design. This is coming again from those early days of air conditioning and cheap energy and perimeter offices. How do you keep everybody comfortable in a building that's got a south face and a north face and a west face and an east face? And the way that has been approached is with an all-in-one, typically an all-in-one HVAC system. So this is a large box sitting up on the roof that's providing heating, cooling, and ventilation to the entire building at all times that any part of the building is occupied. Very large fans to drive that air through miles of ductwork in the buildings. Typically multiple zones that have tight temperature settings, trying to maintain 70, 72 degrees at all times of the year in all parts of the building. The primary method that was used for large buildings has been used is VAV, which relies on reheating in the zones. And at least when I was going to mechanical engineering school in my HVAC classes, the feeling was if some is good, more is better. We do a very detailed job learning how to calculate loads in the building, and then we double. Then my professors say, and then double it, so you've got a safety factor of 2. Very conservative approach towards equipment sizing, and this has really driven those large HVAC loads. And so what you see in a typical commercial building in downtown Seattle and downtown everywhere is this type. If you plot the energy use versus outdoor temperature, it kind of shows you the temperature relationship of the energy use. And you can see there the electric, this is the electric bill. And so that line there represents the base load. So we've got about 17 EUI of continual energy use, which is not related to outdoor temperature. That's the lights, that's the plugs, elevator, basic electrical infrastructure running the building. And then anytime it gets above about 48 degrees, there's a cooling load. The electrical energy starts to go up, which represents, so that wedge there represents the cooling energy in the building. And the gas meter is pretty much all space heating. And this shows for this building, this is a major City of Seattle building. Anytime it's colder than about 67 degrees, the building's in heating. So the vast majority of the year, temperatures are between 48 and 68, and the building is heating and cooling at the same time. And this is how you guarantee that you're going to use a lot of energy for HVAC in a commercial building, is having it be in heating and cooling simultaneously most of the year. Here's the temperature energy graph for a building that we designed, all electric building. So there's no gas meter. This is all electric, and those are now showing the cooling and the heating contributions of the energy use. So it doesn't go into cooling until it's above about 65 degrees outside, and it doesn't go into heating until it's below about 52. So the vast majority of the year, there's no heating or cooling going on. It's just that lighting equipment base load. And if we super insulate a building and drive that heating load way down so that it doesn't require heating until you're below about 45 degrees, now you can see this is how we eliminate the vast majority of the heating and cooling demand on a building, is elimination of that simultaneous heating and cooling, and driving up the efficiency of the envelope to the point where there's very little heating required at all. Then it's a matter of focusing on elimination of fan energy, lights, driving down your equipment loads, and you can start to drive that base load down as was done in the Bullitt Center. I mean, this is how the Bullitt Center gets that energy use down into the teens. Is there is absolutely no simultaneous heating and cooling, super insulation, and good shading almost eliminates the heating and cooling loads.
John, I have a question. This is
Yeah.
Katie. So then, do you have data on what the average indoor air temperature is on that Ecotope design building? Does it stay at 72?
Yeah.
During the cool.
Stays in the 60. This building doesn't have any specialized control over thermostat settings. This is actually the King County Housing Authority's office building down in Tukwila. pretty, I've got a case study. I've got some case study information on it later in the presentation if we get there. But pretty run-of-the-mill office building.
Excellent, thank you.
So to kind of highlight the three main points, the three main things that we need to do to be able to get buildings operating like this is, first of all, we have to move away from these large central HVAC systems that are trying to provide heating, ventilation, and cooling to all parts of the building at all times, so that even if there's just one portion of the building that's occupied, that giant piece of equipment is pumping air through all of those ducts to push air to all parts of the building, regardless of how occupied the building is. And we need to move towards smaller zonal systems that can respond to the loads just in the portion of the building that they're serving. Heat pump technologies are good at that, as well as hydronic systems. Second, we have to move away from this idea of an all-in-one HVAC system where the same box is providing heating, cooling, and ventilation with the same fans sized for whatever the worst case load is, which is typically the worst case cooling load on the hottest day of the year, with the sun blazing down and all the shades up and all the lights on and all the equipment going and the building fully occupied of people. And then double that. That is the size of the box that has to be provided to deliver the ventilation, the heating, and the cooling. So the fans are giant in comparison to what's typically needed. And we need to move towards dedicated ventilation systems, dedicated outdoor air systems that provide ventilation only with heat recovery in small ducts sized just for keeping the air fresh. And this is a photo over my shoulder in my old office. You can see the ventilation being spit in from the corner there. The distribution, instead of ducts driving that to all corners of the office, we use ceiling fans to mix the air. And then the heating and cooling is provided by a ductless heat pump that's only running if there is a call for heating or cooling from the thermostat. Otherwise, it's off. So most of the year, the only thing that's running is that ceiling fan and the heat recovery ventilator. And then occasionally the ductless heat pump cycles to provide a little heating or a little cooling.
I've got a couple of questions from Aaron, John. One was, how does having these many different zonal systems affect maintenance requirements instead of just one big piece of machinery? And then he also was wondering if having mechanical equipment inside the space typically not architecturally desirable, aesthetically desirable. So a couple different to address there.
Yeah, so it's true you've got more boxes to maintain because you've separated the ventilation from your heating and cooling. So you've got a heat recovery ventilator now that needs a separate air filter, but that's really all the heat recovery ventilator is a fan and a heat exchanger with filters that need to be changed. So the maintenance associated with that is pretty small. The distribution, like certainly there's questions about maintenance of like VRF, where you've got a lot of fan coils connected by refrigerant pipes to different parts of the building, but it's not really a lot different than VAV terminal units. The terminal units are really just fans with filters. The bullet center is radiant, so there's nothing showing up in the space there. So in terms of aesthetics, architecturally, there's lots of different approaches. Really, what's necessary is the ability to turn off the heating and cooling terminal units, whatever they are, whether they're radiant floor or baseboards, convectors, or recessed ducted fan coils, or ductless wall units. The primary thing is to separate the ventilation air so that the heating and cooling equipment does not have to run and does not have to be sized to deliver the ventilation. And the ventilation is taking care of itself, because that's really the only thing that needs to be running all the time that the building is occupied. And then the third key aspect of design for off is to right size the mechanical systems. And this means both the ventilation load should be sized to ASHRAE 62, and the heating and cooling loads should be sized to actually what you calculate as a mechanical engineer. And believe the calculations and size to the actual loads. These two photos are similar sized office buildings. This is another City of Seattle office building with railroad car sized HVAC units on the roof, and so much air coming out of the ceiling diffusers that they had to retrofit plexiglass baffles to keep the people's papers from being blown off people's desks. This is, like I say, this is the heating and cooling plant for a similar sized office building in Bremerton that we designed that I'll show a case study of. But size makes a big difference in mechanical energy use. So being true to the ASHRAE standards in design and sizing to that is another critical aspect of design for off. So again, to summarize the three main points, it's separate the ventilation from the heating and cooling and provide that ventilation with a heat recovery ventilator. If that heat recovery ventilator has a high thermal effectiveness, then there's no need for tempering of that air. Just ventilation air running most of the year for most of the building. Second then is zonal heating and cooling equipment. So anything that can be made to cycle on load and turn off, hence the name design for off, turn off whenever there's no call from the thermostat for heating or cooling. And then third is the right sizing of the equipment. And to take it a step further, there's a few other things that are part of this design for off, but those first three get you 80% of the way there. To get the rest of the way there, like I showed on that temperature energy regression graph, high performance envelope to drive the balance point down so that you don't need heating until it gets very cold outside, and you don't need cooling until it gets very hot outside. Focusing on a very high efficiency from the thermal effectiveness from the heat recovery ventilators, allows you to not have any secondary tempering of that air and really turn off that heating and cooling equipment. Having a bit more of a liberal deadband on between heating and cooling is pretty important. Not trying to maintain temperatures between 70 and 72 at all times, but having an elevated cooling set point of perhaps 75 and a heating set point of 70 or even 68. Make sure that you don't have zones that are cycling back and forth between heating and cooling, which we see in a lot of commercial buildings out there. And then turning off the ventilation if nobody's in the space, or at least turning it down when there's only a couple of people in the space based on CO2 levels, can dramatically reduce fan energy. This is has perhaps been considered a no-no during the era of COVID-19, but it's actually been shown that CO2 levels are a pretty good indicator of also COVID concentrations in air, which makes sense. If there's not very many people in the space breathing, there's not going to be much COVID in the air. So I would argue that CO2, even in the age of COVID, can be used to turn down ventilation fans. And then moving the design for off concept to lights, of course, is actually turn the lights off when there's adequate daylight in the space. So okay. Yeah, go ahead.
Right before you moved to this study, we had a question about whether there are different considerations for managing humidity. Now, Cameron didn't say to add or to subtract, but just to manage humidity in the ventilation. Yeah.
It's a good question. I'm sitting here in Seattle, and we have the luxury of never having to worry about humidity. Humidity is not an issue that ever really comes up, regardless of how we were trained in mechanical engineering school. This climate, we do not have to worry about humidity. In the southeast and the northeast in the summertime, humidity is an issue that's going to have to be addressed by the design. And in those, we've actually seen situations in passive house construction where the loads have been driven down so low that the cooling is not coming on, and therefore not dehumidifying the space. So yes, in highly humid climates, the ventilation air has to be treated to address humidity. Let's see. So I wanted to present some case studies now. I'm going to start with the case study that led to our terming our design approach, design for off. And the quote here from Greg Belding is really kind of the key. And this is what he said they did to their building: put a down jacket on it and turned it off. This is Rice Fergus Miller is a architecture firm in Bremerton, and this was their office that we were hired to do, and really kind of knocked it out of the park in a lot of different ways. EUI of 18, so approaching that the same level of efficiency that the Bullitt Center is providing. It's a 3-story office building. It was an adaptive reuse of an old Sears warehouse. very inexpensive, $100 a square foot to take a derelict warehouse and turn it into a super high performance office building, earning, I believe at the time that it was certified, it earned more LEED credits than any other office building in the country, and included a lot of other features like rainwater harvesting, small solar array on the roof. So pretty impressive. I like this photo of Steve Rice, the one of the principals at the time, wondering what the heck he had just done by purchasing this this whole building. But this kind of gives you an idea of what they were starting with. And ended up with, at the time, the most energy efficient office building in the Pacific Northwest. Yeah, one of the highest scoring LEED buildings ever. 95% of their construction waste diverted, $105 a square foot. So how do we get 18 EUI? Super insulation, walls are at R30. Pretty low amount of glazing, 20% glazed, so with triple pane windows, and super high efficiency heat recovery ventilation. Zonal heat pumps, with very little duct work, so there's a 14-foot diameter big ass fan in the main zone doing most of the distribution, and use of natural ventilation during times of the year when the outdoor temperatures are right, and with a system of red lights and green lights to signal the occupants when they should open or close the windows based on outdoor temperature. And this graph shows typical Seattle weather in temperature bins. So the amount of time, the number of hours of the year when the outdoor temperatures are in those different bins. And as is probably not a surprise, there's only a relatively small number of hours that are hot in Seattle, and surprisingly only a relatively small number of hours that it's really cold. Most of the time it's between 45 and 70 degrees, the vast majority of hours of the year. And so we used a passive active approach so that the heating did not come on until it's above about 45 degrees outside. I'm sorry, the heating doesn't come on until it's below about 45 degrees outside. So during about 22% of the hours of the year, sorry, these are, I neglected to say, these are daylight hours. So between 9 and 5, about 22% of those hours are in the heating zone. And so you've got the heat is running and the energy recovery ventilator is running for about 22% of the year. During the times when it's below about 55, just the energy recovery ventilator is on, and then when it's between 55 and 70, we actually shut off the energy recovery ventilator and open all the windows. So this is the passive mode, and that's about 42% of the year. And then cooling is when it gets above 70, the red light comes on, windows get closed, cooling is activated, and the energy recovery ventilator comes back on. So this is like this is our most, I would say, extreme example of design for off, and it shows what you can deliver for an extremely low budget. This is how you get that kind of performance. So this is a cross section of the space. Most of the space is open to itself here. It's got these two big kind of loft, second floor, open to a big central space, so that that big ass fan is running for destratification, and there's windows high and low that are open during that passive mode to drive natural ventilation through the space. And here's a photo of that on the inside. You can see there's no ducts running around the space, just that big ass fan. There's a ductless heat pump on the wall there at the far end. When we came in to the space after it was finished and saw that heat pump right in the center of that artwork, we were shocked and dismayed. But the architect said, no, we wanted it there. We wanted to show that as being the, how small the primary heating system is for the building. There's a few others on the walls over here as well, but very little in the way of infrastructure for that heating and cooling and ventilation, with that big ass fan doing most of the work. And this is then what the energy use looks like during different months of the year. The cooling energy are these tiny little blue slices here in September, August, and July. The heating energy is this purple and peaking in January, and then the rest of it. Green is the lighting, red is that ERV, the fan energy, and then domestic hot water, plugs, computers, miscellaneous is the bulk of the energy use. So the HVAC energy, this is comparison of I think a 2003 CBEX average office. The HVAC loads are these lines that are crammed together here just above 20. Sorry, I should have said earlier, the EUI is about 21.5, and it gets down to 18 with the solar array on the roof. So that 18 EUI includes the effective solar. But you can see that we've just about eliminated the HVAC load in this building. In terms of sizing, much smaller systems than typical. That's how we get that size of system that I showed in comparison to the City of Seattle building with the railroad car sized HVAC units. Heating load was about 12 tons for the 30,000 square foot building. Cooling load about 22 tons peak, even though it hardly gets used. When it's needed, it's just the way that cooling loads tend to go, is they dominate sizing. But still, that 850 square feet per ton, the typical rule of thumb for sizing cooling equipment is 400 square feet a ton, so about half the size of a typical commercial building. And it was cheap, ridiculously cheap. The HVAC, because we drove the loads down so far, HVAC was $10 a square foot. So you don't have to spend massive amounts of money to get these super high performance buildings. And the Steve Rice, the guy pictured with when the building was all falling apart, wondering what he had just done. He actually turned the design of the building over to some of the junior architects there and didn't really realize what they were doing until it was pretty far along. And he was not initially a believer. He was very worried about the design direction. And once it opened, he became our biggest evangelist. He preached design for off all over the place. And when we went to the opening of this building, it was a nice day in the upper 60s. The place was packed. There were more than 100 people standing around on that lower level there. The only thing, we were probably the only people that realized that the HVAC system was forced off, that the only thing running was the big ass fan with the place packed full of people on opening day, and it was perfectly comfortable in there. The architects that work there say that it's the most comfortable building they've ever worked in. So proof is in the feedback from the people that work in the buildings. So I wanted to pause there. I've got several other case studies that I want to present, but wanted to give people a chance to ask any questions now, if there are any, or make any comments.
Yep, there are a couple questions. Just in general, Aaron was wondering if economizers provide similar function to DOAs.
No. The DOAS is really just sized for ASHRAE 62 ventilation levels, just intended to clear out the CO2 that everybody's breathing out into the space. Economizers are really a method for using outdoor air directly to cool the space when the outdoor air is cool and there's a cooling need in the space. And I would argue that if we're designing the buildings right so that they don't need cooling until it gets hot outside, economizers are not very much use. We don't really get very much savings in a well-designed building from an economizer, because you don't need cooling when it's 60 degrees outside, or you shouldn't. You shouldn't need very much cooling when the air outside is cool enough that an economizer is useful. So most of my designs do not include economizers for that reason.
Okay, and then Elisa, I'm sorry if I mispronounced your name, is curious about why zonal heat pumps are the preferred system instead of VRF with heat recovery, where you can just use rejected heat from one zone to heat another zone that calls for heating.
Yeah, so VRF is a form of zonal heat pump, in that it can be controlled to turn off in any zone that it's serving when that zone is not calling for heating or cooling. So the VRF fans do not have to be running all the time, although if you don't pay close attention to the controls, they will be. I'm actually fairly we have done a lot of design with heat recovery VRF. I'm skeptical of how much energy savings we're actually getting from the heat recovery feature, because again, the only time when that becomes useful is if there's heating and cooling happening at the same time in the building. And our whole approach is trying to design the buildings in a way that you don't have one zone in heating and one zone in cooling. Now, there are certainly zones like server rooms that might be in cooling all the time, and you could argue with a VRF system you can recover some of that heat into the other parts of the building when needed. I think the trade-off in energy efficiency of the big valve boxes and the miles of refrigerant pipe that are required for VRF in the space probably negate in a well-designed building the heat recovery that you get from heat recovery VRF. We actually have seen, as we look back to the buildings that we've designed, that the ones that have just heat pump systems versus VRF tend to function as well or better than the heat recovery VRF. But it's certainly a choice that can be used for a design for off approach, just because you can turn each zone off when there's not a call for heating or cooling.
Great. And then Robert,
what I'd like to see is that we move towards hydronic distribution systems and move away from all of the refrigerant piping that we've been putting into buildings with VRF. And you would have to give up on most of that heat recovery, but I don't think we're giving up much.
okay. And then Robert is wondering, in this amazing building in Bremerton, are the windows motorized?
Only the ones that can't be reached. So there's some in the upper clear story that actually, now that I'm saying that, I think they're manual as well. Yeah. So all the windows are manual, and the lights come on to signal people when to open and close the windows. Yeah, I don't know if I had a picture of it, but there's kind of a neat mechanical chain-driven system to open and close the clear story windows.
Yeah, I was just thinking myself that it might be an exciting time when the light goes green and everybody has to get up and open the windows. That's all the questions that we have right now.
Okay.
So do you want to go to another case study? We advertised this as an hour. Seth booked this as an hour and a half so that you would have extra time. So feel free to do another one, and people can stay on if they want. We'll record the whole thing, so if you attendees need to leave, we'll have the rest of this recorded. What's up to you, John?
Well, let's see. I'll show one more case study for a different type of building. So this is fire station in Issaquah. At the time, it was the most efficient fire station in the U.S. I don't know if that's. I suspect that's not true anymore. EUI of 23. The kind of highlights, again, super insulation to separate that heating and cooling time periods, so it doesn't need heating until it gets pretty cold outside. High efficiency heat recovery ventilation. This is a ground source heat pump system that's doing both space heating and cooling and domestic water heating. It's got a fairly substantial solar electric and solar thermal array, although the solar thermal array has never been working very well, and we don't generally recommend it, but that was something that the owner really wanted. And rainwater again. LEED Platinum, we won a first place ASHRAE Technology Award for this one. Actually, first place technology award for the last one as well. One of the surprising things here was how small the geo field ended up being for this building. There's only 8 bores that fit pretty easily in the parking lot, serving 3 identical 5-ton heat pumps, only 2 operating at a time. And again, the sizing ended up being about almost a third of a typical sizing, 1 ton per 1,100 square feet. This is primarily radiant slabs with a seasonal changeover. So the slabs are in heating only for a majority of the year, and then for the summertime, they're switched over to be cooling. And then there's 4-pipe fan coils in the sleeping rooms, so that even in the wintertime, when the firefighters come back after a difficult call, when they tend to be overheated, they can get cooling at any time in their sleeping rooms. This is a photo of the site. You can see that they're drilling for the geo there. So the size of the parking lot compared to the size of the building. So we don't, if you keep the loads under control, you can fit the geo in a pretty small zone. And here's the finished building. Yeah, and so here's some EUI comparisons of this fire station without the contribution of the solar panels compared to other regional stations. About a third of the energy use. And so the question is why, what's happening in those other stations that makes them use 3 times as much energy? Almost all of them have continuous ducted central fan systems that are, again, that heating, ventilation, and air conditioning all from a single box. Most of those other stations are ventilating at about 3 times ASHRAE 62. So they're assuming that the whole building is there. There's really only 6 or 8, maybe 10 or 12 people in that entire building at any time. And a lot of the times there's nobody in there because they're all out at calls. Most fire stations are way over ventilated. Most have no heat recovery, and they've got electric heat tempering the ventilation air, and most of them are overlit with no occupancy sensors on the lights. So design for off approach cuts that by a factor of 3. I don't know if there's any other questions. We're at time.
Yeah, we do have a couple of questions.
Okay.
There was somebody wanted to know about the issues you have with solar thermal.
Well, it takes a lot of maintenance to keep solar thermal systems operating. I don't know of a solar thermal system that is working right. We've designed a few over the years, and they all end up not getting adequate service and being taken out of service. So this one was piped backwards. A piece of it was piped backwards. The commissioning agent did not catch it. And so it froze and dumped its load of glycol and water all over the roof. They tried to fix it a few times, but solar thermal systems are extremely hard to maintain and keep working in our climate. Maybe in Southern California they're a great idea, but we don't advocate them up here anymore. If you're going to buy solar electric. It works great.
Got it. Okay. And then Cameron also was wondering, in regard to both the case studies To what degree are the designs also decreasing embodied carbon?
The very little. I mean, the mechanical systems themselves are a lot smaller. The pieces of equipment are smaller. The heat pumps are smaller. The amount of refrigerant ends up being smaller. There's less duct work. But the buildings are very similar. And in some cases, maybe you could argue that there's more embodied carbon because we're insulating them more. So to address embodied carbon is really, that one is still firmly in the field of the architects. So earlier I said that it's not the architect's problem anymore. I take that back. The architects have a new target. It's not so much the energy efficiency. It's really the embodied carbon. That's the architect's new big challenge. Energy efficiency is all for the mechanical engineers, but embodied carbon's all for the architects.
All right, and we have one more question. It's maybe a big one. How do these systems scale for larger buildings, or do you have some larger buildings case studies?
The only high rises that we've designed are multifamily, and the issues for the mechanical systems are pretty different in a multifamily building, because, well, just because they're very different. So Ecotope doesn't have any high-rise case studies for design for off. But certainly all the same concepts apply. If I were to do a high-rise office, I would probably look at floor-by-floor ERVs, so that if that floor was not occupied, you could turn the ventilation off. And then some type of zonal, ideally a hydronic combination of hydronic fan coils or radiant hydronic for the heating and cooling. So there's no reason that any of these concepts don't translate to high-rise buildings. I just don't happen to have one that I can show you that we've done.
All right, that's all we have for questions. And most attendees have stayed on, just so you know. You're doing a really great presentation.
I mean, I have a couple other. I'll do one more case study, just because I think it's a neat one. The next one I've got on here is from Sitka, Alaska. This is their public library. It was a major renovation. They were operating on fuel oil. All of the city buildings were operating on fuel oil, which is mined in Alaska, shipped down to Washington State for refining, and then barged back up to Alaska and sold to all these towns along the coast. So they're spending a lot of their money is leaving the community, and most of them, including Sitka, have their own hydroelectric plant for electricity generation. So Sitka had invested to increase the capacity of their local hydro plant, which the city owned, and then they're spending all their money on fuel oil and sending it out. So this was a way to get them off of fuel oil and onto their own clean electricity. And we, again, this was cut the energy use by a factor of 3 from the old library operating at an EUI of 99 to an EUI of 32. They added about 50%. They increased the size of the library by about 50%. And the focus again was on creating a very high performance envelope. We did use a VRF system here, although primarily in a radiant floor distribution system. and very high efficiency dedicated outdoor air system, heat pump water heater, and another first place ASHRAE Technology Award for this one. That's the old library, that's the new one. This is like the public building in Sitka, Alaska. This is where the community hangs out in the dark, cold winters, is the public library. So this was a pretty important building for the town. You can see there's not a lot of ductwork blowing around this space. You can see one of the small ventilation grills up on that up in the upper left there, and that's about it, with the radiant floor supplying the heating and cooling to the primary space. This is a graph of the energy use. You can see in the upper graph there the big peaks of oil usage in the wintertime, and the very small peak of electricity usage in the summertime. So not a lot of cooling in this space. And after the renovation, it's really very flat energy use. There's not a significant heating peak showing up in the energy graph. And they cut their cost. They increased the size of the library by 50%, and at the same time cut their costs in half for operational costs. And here's the temperature energy regression graph again. You can see that the slope of the heating line is much lower based on all of the insulation that was added, and the electricity only increased by about a quarter, while the size of the library went up 50%, and the oil was completely eliminated. And again, so a comparison to some of the other typical libraries. A third of the 2003 CBACs, a third of their old library, about half of Seattle average library energy use for this building. And I guess just since I'm rolling and people are still listening, I'll keep going. I'll show a couple more. This is
John,
what's that?
Cameron had a question about the radiant heating on the library. Does the circulation, is there a significant amount of circulation just from the changing air temps there?
I'm not sure I understand the question. Circulation
in the radiant floor heat.
Since the building is so well insulated, the radiant floor it changes very slowly, because it's a fairly significant slab. So there's not a lot of temperature swing at all in the space. I'm not sure I totally understand the question.
I bet Cameron will clarify. Maybe go on to the next case study.
Okay, so this is King County Housing Authority building down in Tukwila. I showed the temperature energy regression graph earlier in the presentation. EUI of 26. Again, this was their new office across the street from their old office, which is using about 3 times as much energy. Not super insulated. We were not able to really impact the performance of the envelope in this case. So it has an uninsulated slab, not very good double glazed windows, not very good walls or roof. So that 26 EUI is not because it's super insulated. No economizers. getting back to that economizer question earlier, no energy savings from economizers. No DDC system. This is just using the thermostats coming with the heat pump system. There are pretty decent lights and plugs. This was several years ago, so lighting has continued to improve, but pretty good lighting design and relatively low plug loads in the space. We are using the VRF with heat recovery in this space, so pretty standard ceiling cassette design. And then the dedicated outdoor air system used a very high efficiency cross-flow heat exchanger core that we designed up with super efficient fans. And so again, that's most of the time, that's the only thing that's running in the space. There's no operable windows in this building either, so it's anytime it's occupied, that energy recovery ventilator is running. So again, we drive the HVAC energy down to, what is this, about 25% of the energy use is HVAC, because the building is not very well insulated, and we're not able to utilize any passive mode, but extremely inexpensive. $14 a square foot for the HVAC, so you don't have to. This is kind of, in my mind, the case study that shows how you can achieve this with just the simple design for off concepts, very inexpensively end up with a building that uses a third of typical. And again, this is just kind of another example of showing that HVAC load and the impact that you can have on it compared to typical design. And here's that RFM building again. So the reason that RFM is at 4 and King County Housing Authority is at 7 is that's the impact of the envelope. That's the impact of that super insulation. And yeah, I'll maybe not talk through that slide. I've got one more case study I'll quickly give since there's still people listening. This is in West Seattle, West Side School. This was an adaptive reuse of a church. They didn't have a big budget, but they wanted to focus on energy efficiency, so it's right up our alley. Again, small, here we used small zonal dedicated outdoor air systems, so a heat recovery ventilator per classroom with CO2 control, heat pumps, ductless heat pumps per classroom, and heat pump water heating. This kind of shows what was done to the building. And here's a picture of the classroom with the mechanical. So ductless heat pump, ventilation air from a heat recovery ventilator installed over the corridor, and ceiling fans. So very simple, very inexpensive, and it ended up with super energy efficient school. EUI of 14. HVAC, again, very low. So there's a comparison to the old school. So the kind of key takeaways are the envelopes are important, but HVAC is really where the energy is at. Need a system that can be turned off right-sized. Net zero energy is within reach if you do those things. The heat pump water heating was pretty inexpensive in this building too, and don't bother with the tempering of the dedicated outdoor air system if you pay close attention to the efficiency of the thermal effectiveness of that heat pump. So that's the recap. Thanks everybody for hanging in there for a little extra time. If there's any more questions, I'll take some last few questions, and then we'll be done.
There aren't any more questions. Oh, I've gotten out of center here. There we go. This is great, John. Did you have contact information for people to contact you, or do you want us? There we go. Nope.
I don't have it on my
email
slide, but yeah.
Email
John?
the Lighting Design Lab and we'll pass it on to John. It's lightingdesignlab@seattle.gov. That's absolutely fine. And just real quick, I'm gonna let everybody know about some city light incentives are increased. Speaking of, oops, previous lighting controls, insulation. So right now that you're inspired by all the work that Ecotope has done pretty cheaply, give Seattle City Light a call and see if any of these projects can get some extra incentives toward them. And that is all I have too. Thank you, John. That was really great. We haven't had a webinar like that focusing on kind of whole building systems. So that was awesome. Thank you. Thanks everybody for attending, and give us a visit at lightingdesignlab.com and see what's coming up.
Thanks for listening, everyone.